As blockchain adoption accelerates, scalability, transaction speed, and cost have become major bottlenecks. To address these challenges, developers have engineered a layered approach: Layer 1 and Layer 2 blockchain solutions. Layer 1 represents the base layer, the actual blockchain like Ethereum, Bitcoin, or Solana, while Layer 2 sits on top of these networks to enhance performance and reduce congestion. Understanding the differences between these layers is essential for investors, developers, and users alike, as each serves a unique role in the blockchain ecosystem. This video outlines the top 10 differences between Layer 1 and Layer 2 blockchain solutions, providing clarity on how they interact, their technical distinctions, and their impact on the future of decentralized technology. 1. Definition and role in the ecosystem. Layer 1 blockchains refer to the foundational blockchain architecture, Bitcoin, Ethereum, Cardano, etc., that handle consensus, data availability, and transaction validation on-chain. They are the base networks responsible for processing and storing all transactions. Layer 2 blockchains, in contrast, are protocols built on top of Layer 1s to improve scalability and efficiency. Their job is to offload processing from the base layer while relying on Layer 1 for security and final settlement. 2. Scalability, focus, and performance. One of the most fundamental differences lies in scalability. Layer 1 chain like Ethereum can handle around 15 to 30 transactions per second, TPS, due to consensus limitations. This becomes a bottleneck as demand rises. Layer 2 solutions, such as optimistic rollups, ZK rollups, or state channels, are specifically designed to scale transaction throughput, reaching hundreds or even thousands of TPS by executing transactions off-chain or batching them before settling on Layer 1. 3. Transaction costs. Layer 1 blockchains often suffer from high transaction fees during peak usage periods. For instance, gas fees on Ethereum can spike dramatically when the network is congested. Layer 2s are built to address this by processing multiple transactions off-chain and then submitting a single batch back to the mainnet, reducing individual transaction fees. This cost efficiency is crucial for DeFi applications and NFT platforms that need frequent, low-cost interactions. 4. Security and finality. Layer 1 chain are considered more secure as they enforce consensus directly on the main network, often using proof-of-work or proof-of-stake mechanisms. Security is built into the protocol and enforced by thousands of nodes. Layer 2s inherit this security model indirectly by anchoring their data to the base layer. However, certain Layer 2 types, like sidechains, maintain their own consensus mechanisms and are therefore more vulnerable if improperly designed. 5. Consensus mechanisms. Layer 1 networks include consensus algorithms as part of their core protocol. Bitcoin uses proof-of-work, Ethereum now uses proof-of-stake, and other networks explore delegated proof-of-stake or other models. Layer 2s do not typically have independent consensus. They rely on Layer 1 for finalizing state changes. Instead, they use methods like fraud proofs, in optimistic rollups, or validity proofs, in ZK rollups, to ensure integrity before submitting data back to the base layer. 6. Interoperability and flexibility. Layer 2 solutions are more flexible and easier to modify since they are not limited by the same consensus and governance constraints as Layer 1 chain. Developers can experiment with new technologies, scaling strategies, or smart contract designs without altering the core blockchain. However, this flexibility can be a double-edged sword. Some Layer 2s have fragmented user experiences and are not always interoperable with other DApps and protocols. 7. Deployment complexity. Deploying changes or upgrades to Layer 1 chain requires consensus from validators, community approval, and often a hard or soft fork. This process can be slow and contentious. Layer 2 upgrades, on the other hand, can be rolled out faster because they're built separately from the mainnet. Developers can iterate more quickly and push improvements without major disruption, enabling rapid innovation and experimentation. 8. Examples of each layer. Well-known Layer 1 blockchains include Bitcoin, Ethereum, Solana, Avalanche, and Cardano. These are complete networks with native tokens and built-in consensus. Layer 2 solutions include Optimism, Arbitrum, ZKSYNC, StarkNet, and Polygon, originally a sidechain but now expanding into ZK rollup territory. Each Layer 2 project brings unique approaches to solving congestion, with varying degrees of decentralization and user adoption. 9. User experience and speed. Transactions on Layer 1 are often slower and subject to confirmation times that may range from seconds to minutes. This lag can hinder real-time applications like gaming or high-frequency trading. Layer 2 networks drastically improve the user experience by enabling near-instant finality, lower latency, and smoother interfaces. Wallet integrations, bridges, and app support are key components improving Layer 2 adoption among end users. 10. Future outlook and coexistence. Layer 1 and Layer 2 solutions are not competitors. They are partners in building a more scalable blockchain ecosystem. As Ethereum continues its roadmap, including sharding, Layer 2s are expected to play an even more vital role in scaling Web3. Layer 1s will focus on decentralization and security, while Layer 2s will focus on scale and speed. The future likely includes a layered ecosystem where users interact seamlessly across levels without needing to understand the technical details behind the scenes. Understanding the differences between Layer 1 and Layer 2 solutions is essential for anyone involved in blockchain, whether you're an investor, developer, or end user. Layer 1 is the foundational infrastructure, offering decentralization and security. Layer 2s are innovation layers designed to improve speed, scalability, and cost-effectiveness. Together, they provide a scalable, efficient, and robust framework that can handle mass adoption of decentralized applications. As blockchain technology matures, the seamless integration of these layers will shape the future of Web3, enabling faster transactions, broader use cases, and greater global impact.